let's see if this starts working. All right, so welcome to Math341 probability. This is lecture number 4. Okay, good. It looks like it is recording. All right. So what we want to do today is we want to continue our discussion on what should the axioms of probability be. We have some intuitions, and we want to make it somewhat rigorous. If we were to make it fully rigorous, we would have to take a class in real analysis, and we do not want to go to that extreme at this point. Okay? So, wish list. So we have the empty set, we have the whole space, and we have things such as A. And we want to talk about probabilities. So what would you want the probability of the empty set to be? You'd want that to be 0. What would you want the probability of the whole space to be? 1. And what about the probability of any event A?
0.
It should be between 0 and 1. So we'll say it's in the interval 0, 1. And now the interesting one is the probability of a union. Of the union of the AIs. And we'll have I goes from 1 to infinity. We want that to be the sum, I goes from 1 to infinity, of the probability of the AIs if pairwise disjoint. So what it means to be pairwise disjoint is no two A's have an element in common. If X is in A5, it's not in A6 or A7 or A8. This is very similar to the bird problem where we split it up into lots of different things. Okay? So this is essentially our wish list. And we talked about why we can't have a general union, because if we had an uncountable union, what would we assign the probability of a singleton to? And we said that there was no consistent assignment. All right. Now, let's let omega be our outcome space. We're going to need to choose events, and then to those events we're going to need to assign probabilities. And there's lots of different ways you can do this. We start off with a very simple example. I will take a coin. Since this is one of my coins, I will assume I have modified the coin and it's no longer fair. So it has a certain probability of heads, a certain probability of tails. So maybe probability of a head will be 0.7, and what will the probability of a tail be? Yeah, it should be 1 minus that, 0.3 if you don't want to do the arithmetic. We will assume the coin is not going to land on a side. It will always land on a head or a tail. And let's say we toss it 3 times. And we'll say the tosses are independent. Okay? So the outcome of one toss has nothing to do with the other. So how many different strings of heads and tails could I have? Yes?
You have 6, right?
Not 6. Close to 6, but not quite. I could have 8. I have 2 choices for the first. I can have a head or a tail. And then for each one of these, I could have a head or a tail. And then for each one of these, head, tail, head, tail, head, tail, head, tail. So if I look at it like this, I would have 8 possibilities. And I can try to assign probabilities to each string. You know, the string head, 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 the string head, head, tail, etc., etc., etc. And so I could choose my outcome space to be head, 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 all the way down to tail, tail, tail. And so if I do this, I will now have 8 different events, and I would have to assign a probability to each of the 8 events. I might choose different ways of looking at things. I might choose a different outcome space. For a lot of times, I don't necessarily care if it's head, head, tail, or head, tail, head. I just care how many heads do I get. So there's more than one choice of outcome space. It depends on what you want to study. For a lot of things, I might only care about the number of heads. And so what I might do is I might say, X, and I'm going to jump the gun a little bit, is a random variable It'll be the number of heads. And then what are the possible values? 0, 1, 2, 3. So maybe actually I should make my outcome space 0, 1, 2, and 3, and just figure out how should I assign probabilities to those 3 numbers, or to those 4 numbers. We will see later in the semester that it's much better to work with numbers than to work with things like heads and tails. What's 3 plus 5? 8. What's 2 heads plus a tail? 2 heads and a tail. You can't simplify it further. You can't do arithmetic operations on heads and tails. But we can add numbers. So this is why we always want the quantities we're looking at. We love working with real numbers because then we can add. So for something like this, typically, let's make a head a 1 and a tail would either be a 0 or a -1, depending on what you're looking at. For something like this, we'd probably have tails be 0, heads would be 1, and then for each one of these, I would have a function. You give me a string of 3 tosses, and it will return the number of heads. So now I need to figure out what are the probabilities of these. Well, one way is to just do it by brute force counting. How many, do we agree that all of these paths are equally likely? No. Why aren't they equally likely? It's not a fair coin. If it was a fair coin, then it'd be very easy. The probability of all tails, which would be no heads, would just be 1/8. The probability of exactly 1, and you would just keep adding them all up. So now it's a little bit more involved, but it's not too bad. So we want to calculate what is the probability that we get a value of 1. So it would be essentially the probability of head, tail, 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 head, tail, and then tail, tail, head. So each one of these, this would be 0.7 times 0.3 squared plus 0.7 times 0.3 squared plus 0.7 times 0.3 squared. Because each one of these has 1 head and 2 tails. And then you can just calculate and add it this way. Another way you could look at this if you're comfortable with some of the combinatorics is I have 3 tosses and one of the tosses must be a head. The one that's a head now gives me a 0.7. And I have that to the first power because I have 1 head. And then being exceptionally pedantic, then I have a not head, which happens with probability 1 minus 0.7. And the number of not heads, being extremely pedantic, is 3 minus 1. Right? That's another way of doing it. Right. I'm going to show you a third way of doing this. This is the expected counts approach. There we go. Okay. So the last is the expected counts approach.
Professor, it went back the other way as soon as you turned around.
Ah, thank you. All right. So let's look at the expected counts. I want to start off with some number of coins, and I'm going to just keep tossing them and see what happens. What do you think would be a good number of coins to start off with my initial set of tosses? And then I'm going to just count and see what fraction of these tosses are going to be exactly 1 head. So my probabilities are 0.7 and 0.3. What might be a good number with 0.7 and 0.3? 10. So 10 would be really good because if I toss 10 coins, I would expect 7 to be heads and 3 to be tails. But then I want to do my next round of tosses, right? Because I want to do 3 tosses. So if I did it only 10 times, by the time I get to my next toss, things would be now fractions. You can do that, but I think it's cleaner to have a number larger than 10. What number might be a good number to do? 1,000. So we start off with 1,000. And on the first toss, how many of them are heads? 700. So we have 700 that are heads and 300 that are tails. On the next toss, how many of these are heads? 490 are heads. And I'll call this HH because it's double head. How many of these are head-tail? 210. Now over here, of these, how many of these become tail-head? 210. So these are actually really together, right? I should call that 420 head-tail and just make my life a little bit easier. And then how many of them are tail-tail? 90. What can we do right now to check and make sure we haven't made a mistake? Add them up. Good. Does it add up to 1,000? Does this mean we haven't made a mistake? No. But it at least gives us some hope that we've done the algebra correctly. Right? So it's nice. Check. Good. All right. We want to calculate the probability we have exactly one head. Do I need to do anything with this? No. It's already got two heads. I mean, for completeness, I could do this and get, the whatever is head, 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 and whatever is head, head, tail, but I don't care. Do I have to worry about this one? Yeah. Which one do I need to worry about? Only the one that's tail. And so the one that would be tail is I'd multiply this by 0.3. So it should be 126. And then for this one, I would only care about multiplying by 0.7, and that would be 63. Head, tail, tail. So it would be 126 plus 63 divided by 1,000. So hopefully we haven't made any algebra mistakes. But this is another way to try to get a probability of something like this, is to form a tree diagram like this and just go through and say, I'm going to just do this a huge number of times. I'll do it 1,000 times, and I'll look and see what % of the time do I end up in the cell I want to. What % of the time do I end up with exactly one head? And that would be 126 plus 63 over 1,000 if I haven't made any algebra mistakes. Okay. Any questions on this? As the problems get more and more involved, you see you really don't want to be drawing the long trees like this. You'd much rather do something nice like this using binomial coefficients. But it's nice to know that there are more than one ways you can approach this. All right. So what I want to do now is I want to turn to section 2.4 to Kolmogorov's axioms. And so essentially a lot of our wish list is going to become axiomatized. But the biggest problem is limiting what we are going to discuss. We are not going to be discussing arbitrary events. We are only going to be discussing very specific types of events. And that is one of the great insights. And what's lurking in the background is measure theory. So we will always be working with a triple. So this is section 2.4, Kolmogorov's axioms. So we have a probability space. It's going to be omega, sigma, and PR. The notation is a little bit unfortunate. So the omega, that's our outcome space. Sigma is what's called a sigma algebra. It's not a sum. It is the capital of the little sigma. And what this basically means is these are the sets to which you assign probabilities. Sets which we assign probabilities to. For us, we should think of sigma as intervals or discrete sets of points. But if you take measure theory, you will then have a more extensive set that you can look at. And then the last is this is our probability function. Assigns real numbers in the interval 0, 1. So when you make a probability assignment, you are always going to get something between 0 and 1. Okay? And if I ask you to find a probability of something, I can only give you things that are in the sigma algebras. So mathematicians have a lot of fun trying to consider what are the possible sigma algebras you can look at. And you want your sigma algebra to have certain nice properties. If you have two things in the sigma algebra, their union and their intersection should be in the sigma algebra. And then maybe you might want to talk about finite unions and finite intersections, okay? What about countable unions and countable intersections? And you can start playing games. And you can see, if I start off with the intervals, what kind of spaces does it generate? We're not going to really worry about that. We're going to just say discrete sets of points, intervals, and just leave it at that and be happy. All right? So now it's ready to start introducing the axioms. So the first is, if A is in your sigma algebra, then the probability of A is in 0, 1. We need something like that. Right? The only possible values is going to be something between 0 and 1. The next axiom is the probability of the empty set is 0, and the probability of everything is 1. Again, a very reasonable thing to add. And then the last one is if the set of AI is at most countable. What that means is it's either a finite collection or it's a countable collection. And pairwise disjoint. Then the probability of the union of the AI is the sum of the probability of the AI. I'm not going to write I goes from 1 to infinity because I want to allow myself to deal with just finite unions. If you want to use unified notation, you could actually just make all the AIs empty from some point onward. If you have two empty sets, are they pairwise disjoint? What does it mean for two sets to be pairwise disjoint? They have 0 elements in common. How many elements does the empty set have? 0 elements. So it can't have an element in common with anything because it has no elements. So the empty set is trivially disjoint from every other set. Is the empty set disjoint from itself? How many people say yes? I would say if you look at the definition, there are no elements in common, so the empty set is disjoint from itself. Okay? So these are Kolmogorov's axioms. Okay? This is essentially our wish list with the restriction that we only deal with countable. Okay? Yes?
So for number 1, if A belongs to sigma, why
Yes.
not A belongs to omega?
So the sigma algebra is going to be subsets of omega. These are the events that we assign probabilities to. So let's do some examples. So one possible sigma algebra, this is the stupidest of all sigma algebras. This is the most trivial of all sigma algebras. You only have two sets, the empty set and omega. So either nothing happens or something happened. So if you go through, it's very easy to check that all of these hold. Your only possible choice of A is the empty set or omega. A lot of times you unfortunately have these trivialities. Everybody here is supposed to have taken linear algebra. You've done vector spaces. What if you have the empty set? Is the empty set a vector space? It doesn't have a 0 element. So what if you just consider the space of just the 0 element? That's a vector space. It's a vector space with only one element, the 0 element. And I remember there are some theorems that are slightly different if you are looking at the set that is just the vector space of 0. And my freshman math book said, we will tacitly exclude that whenever it causes trouble. They never said when it caused trouble. They just said, if it causes trouble, ignore it. That's not good writing. You want to be clear and say what you are always studying. if you're proving something about a probability space, is this true for all probability spaces, or is it true only for probability spaces with certain properties? This is absolutely fine as a triple, and our probability function would just assign the value of 1 to omega and 0 to the empty set. All right, a more interesting one is assume omega is finite. Then P of omega is the power set. So the power set is the set of all subsets. So set of all subsets. So if omega has, say, 3 elements, then the power set of omega has how many elements? 8. And in fact, we just did this a moment ago. That's why I chose 3. For every element in omega, you take it or you don't. You take it or you don't. You take it or you don't. And so, in general, the size of the power set of omega is equal to 2 to the size of omega. Okay? If you think about the integers, if you take omega to be the integers, then the power set is going to be the set of all infinite strings of integers. That's the real numbers. And you actually have as a deep result that this is a different size infinity. This was the Cantor diagonalization we did. This is a strictly larger infinity. So if you take the integers, if you take omega to be, say, the natural numbers, then the size of omega is the lowest infinity, aleph naught. Now this is just an advanced aside. If you then look at the reals, which would be 2 to the natural numbers, and for its size, the question a lot of people asked is that the next largest infinity? Some of you are smiling, so some of you know the answer. The answer is whatever you want it to be. It turns out that this assumption is independent of all the other axioms in set theory. You can take it or leave it. And there's a lot of strange things you can put here. In mathematics, you call your thesis advisor your father or mother. Your thesis advisor's advisor would be your grandfather or grandmother. One of my grandfathers is Paul Cohen, who was the one who finally resolved this question. It is not necessary for what we're doing. All that I really want you to know is that there are orders of infinity, and the power set is always going to be larger. For finite sets, it's clear that the power set is larger than the set. But for infinite sets, it's true as well. And so now, let's look at the power set. So it's the set of all subsets. And what we might want to do, if it's finite, is maybe say the probability of A is equal to the number of elements in A divided by the number of elements in omega. That's a really good way to assign a probability. This would be essentially the uniform probability. Right? This would be if we had a fair coin, and I would just care how many strings have exactly one head. Then that would be head, tail, 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 head, tail, 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 head. So I'd have 3 strings divided by 8, I'd get 3 8s. With a biased coin of 0.7, I'm no longer going to get 3 8s. But this is the simplest one I could do, and now I can change probabilities to just counting how often things happen. So a lot of probability is counting. That's why for the first week or 2, we're going to be doing a lot of combinatorics and a lot of counting. If we have infinitely many elements in omega, I can't do this anymore. So you can't put a uniform distribution. I know somebody had mentioned this in an earlier class. You can't have all the integers equally likely to be chosen. There has to be some decay as you go further and further and further. Okay. Any questions in what we've done so far? So right now we're basically just stating some of the axioms. What we're going to do is we're going to look at some of the consequences, and then what I want to, yes?
So the power set of omega, like let's say it had 3 elements in it.
Yep.
And then we're saying the size of that is 8.
Right, so for instance, let's say omega is A1, A2, A3. Then here is the power set. It could be empty.
Right.
It could be A1, A2, A3, A1, A2, A1, A3, A2, A3, A1, A2, A3. So those would be all the possible, and so I'll just put a curly brace here, a brace here, and then just put in some commas. So the reason it's 2 is because for each element you either choose or you don't, you choose or you don't. And that's where the 2 to the omega comes from. Good?
Yeah.
Okay, so now we'll prove one consequence of Kolmogorov's laws, and then what I want to do is I want to talk about how to sniff out formulas. So a lot of times if somebody gives you a formula, okay, you can use it, but it's how would you find that formula yourself? Okay? And we'll go back and review some things from Calc 1 to try to build up intuition. Most of you are not going to use most of the material we will cover in this course. You're just not going to be in situations where you're going to have to be doing these calculations. What you will use from this course is how to think about problems, how to approach things. And that's why I really want to emphasize how do you try to find what you're trying to prove. All right, so first, we'll just do a nice lemma. So there's a couple of ways of phrasing this. I think they'd like to say the law of total probability. Yes. The law of total probability. So the probability of A plus the probability of not A is 1. This essentially falls under the blatantly obvious section of the book, right? If A happens, then not A doesn't happen. If not A happens, then A can't happen. But we want to prove this rigorously, and we want to prove this using Kolmogorov's laws. So we want to use the axioms. Okay, so what do we know? Well, we know the probability of the entire space is 1. We know the probability that nothing happens is 0. And we know that the probability of a disjoint union is the sum of the probabilities. So is there any way to write omega as a disjoint union involving A and A complement? Yes, in fact, omega is just going to be A union A complement, and it's disjoint. This is what it means to be A complement. You have nothing in common with A. So then the probability of omega is the probability of A plus the probability of A complement because they're disjoint. And the probability of omega is 1. So this equals 1, and so that's our proof. Probability of A plus probability of A complement. If you haven't seen this notation before, a filled-in box is basically the QED symbol. That which was to be proven, we finished. It's just a way of marking where you are in the argument. Okay. Any questions on this? All right. So I want to leave up Kolmogorov's laws. And so I want to return to calculus. So in the last class, I asked you to create a wish list, and I asked you if you could choose the product rule, what would you choose? And we all agree that if we could choose things, we would have the derivative of a product is the product of the derivative, and definitely the derivative of a quotient is the quotient of the derivatives. Right. Does everybody remember the product rule and the quotient rule? Okay. Sometimes you forget things, but you remember some of it, or you remember most of it. If you remember most of it, you can often sniff out what the right answer is by looking at some special cases. And so the question is there a way to sniff out what the product rule is? And so what I want to do now is I want to discover the product rule experimentally. And then I'll apply that thinking to try to discover some probability laws. So, product rule. So I want to choose nice functions f, g, and then a of x, which will be f of x times g of x. So I get to choose whatever functions I want to look at, but they've got to be functions such that I can take all the derivatives easily. Anybody have a good thought for what f of x should be? X squared. More generally, I can try x to the nth power. What would be a good choice for g of x? Yes? I'm sorry? X to the nth power. And then their product would be x to the n plus n. So these will all be very easy functions for me to differentiate. I get f prime of x is n x to the n minus 1. G prime of x is m x to the n minus 1. And a prime of x is n plus m x to the n plus m minus 1. And so now, these are my inputs. I have f, g, f prime, and g prime. And so I want to use f, g, f prime, and g prime somehow to get the derivative of fg. Well, I noticed that I have to have x to the n plus m minus 1 power. How could I get something to the n plus m minus 1 power? Yes? Yeah, multiplying diagonally. I could take f times g prime, or I could take g times f prime. So if I look at f prime of x, g of x, plus f of x, g prime of x, that's going to be n x to the n plus m minus 1 plus m x to the n plus m minus 1, which is n plus m x to the n plus m minus 1. Is this a proof? No. But you feel confident now that you might have discovered the product rule. You're getting some intuition. So for those of you who have seen this before, please do not speak up. All right? I will wait a second so you can try to think exactly. Okay, so some of you now know exactly what I'm about to do. All right? I want to test people's algebra skills. All right? How do people feel about algebra? 16 divided by 64 in lowest terms. Go! All right, that was pretty fast. 19 over 95 in lowest terms. Amazing. Very good. 49 over 98 in lowest terms. Sorry? 1/2, yep. Let's do one more. 12 over 24 in lowest terms. I get 1/4. 12 over. Right.
Wait, what?
All right. People remember how to do long division? Let's check this, okay? Well, actually, rather than doing long division, I'm going to just do fast division. 16 over 64, I cancel the 6's and I get 1/4. 19 over 95, I cancel the 9's and I get 1/5. 49 over 98, I cancel the 9's, which is 4/8, which when I reduce is 2/4, which when I reduce further is 1/2. So clearly, since it works 3 times, the way you divide two two-digit numbers, if the anti-diagonal is equal, is to cancel the anti-diagonal. And so 12 over 24 must be 1/4. So I do this deliberately in almost all of my classes to just really drive home the point that just because you check something a few times does not mean you've proved it. At least not in this department. There are other places on campus where that's more than sufficient. And in fact, they would go, why did you even bother doing it once? But here, there's no such thing as proof by example. This proof by exhaustion. Proof by exhaustion is when you go through every possible case and you show it works for every possible case. That's fine. But you can't prove something by just checking a few cases. That doesn't mean it's a bad idea to check a few cases. This is a great way to build intuition, and it's a great way to see what the answer might be. Okay? All right. So what I want to do now is I want to find a formula for the probability of a union. And the idea is I want to express the probability of a union in terms of probabilities of nice events. So I want the probability of A union B. And I have A, B, and what's another natural set I might have related to A and B? A intersects B. So I'm going to guess the following formula. I'm going to guess the probability of A union B is going to be C0 plus C1 probability of A plus C2 probability of B plus C3 probability of A intersects B. And I think it still makes it, yes, it all makes it on the screen. So I'm guessing that the probability is a linear combination of these basic events. What we're about to do is not a proof, but it's going to be trying to sniff out what's the only linear combination that has a chance of being correct. And then we'll prove that that's actually correct. So whatever you have something like this, you should always be thinking of extreme cases. For all the times in your life when you've wanted to be a smartass, this is your chance to indulge your inner child. You can give me the most trivial extreme cases you want, because I need those now. It's got to hold for everything. It's got to hold for those. You got to give me a choice of A and B. What do you think might be a good choice of A and B? Yes? They're both empty. Well, the probability of A will be 0, the probability of B will be 0, the probability of A intersect B will be 0. So what can we deduce if we take empty, empty? C0, 0. Okay? Not bad. So, gone. Okay. What would be another good thing to choose? Yes?
A and B are the same set.
So we could take AB will be AA. And now in this case, we would get C1, the probability of A, plus C2, which is the probability of A, plus C3, which is also the probability of A. So we get C1 plus C2 plus C3 times the probability of A is the probability of A. Because A union A is just A. So what can we deduce about C1 plus C2 plus C3? So C1 plus C2 plus C3 equals 1. Do we know that all the C's are positive? No. I need more good choices. There's at least one more good choice that hasn't been said. Yes?
Probability B is 0.
Yeah.
Probability of A is none.
So let's choose A, and then you've got to give me an explicit choice for B. What's a good choice for B? The empty set. So if we take B to be the empty set, then we know the probability of B is 0. We know the probability of A intersect B is 0. So what can we deduce from this? I'm sorry? So then we would get the probability of A is C1 times the probability of A. So we get C1 equals 1. All right, well, if we could take AB equals A empty, what else could we do? Yeah, we could do it the other way. We could do AB is empty B, and that will get us C2 is 1. And now that we know C1 is 1 and we know C2 is 1, what can we deduce? Yes, now we know C3 is minus 1. So when we put this all together, the only possibility that will work is going to be probability of A plus probability of B minus the probability of A intersects B. Again, this is not a proof, but it's at least a way to sniff it out. How many of you have seen a proof of the Pythagorean formula? How many of you have seen at least 2 proofs? 10 proofs. How many of you know the only US president to be credited with a proof? Yes. Garfield. So, and where did Garfield go to school? He went here. Anybody know how Garfield died? Coming here for a reunion. So I just want you to be warned, if any of you do become president, just be careful traveling back here for your reunion. It's debatable whether or not Garfield should get full credit for this proof. I think it's very similar to some of the other proofs I've seen, but he is officially credited with a proof of the Pythagorean formula. You could apply ideas like this and sniff out that if you're going to have a right triangle with A, B, and C, that the only thing that would work is A squared plus B squared equals C squared. It's not a proof, but you can sniff it out. And if people are interested, email me and I will give you a reading or a video I've done on just that. What I want to do now is I want to prove this, and now that we have an idea of what things are, this gives us an idea of how to prove it. So I've been carefully trying to leave Kolmogorov's axioms on the board so that they will still be available for us. And so we don't really have that much at our disposal. We have probabilities of events are in 0, 1. The empty set is 0. The full space is 1. And if we have a disjoint union that's at most countable, then the probability of the union is the sum of the probabilities. So we love disjoint unions. So the question is, we want to take A union B. So sometimes people like to draw Venn diagrams. So here is my space omega. Here is A. Here is B. Here is A intersect B. And then this whole thing would be A union B. So we want to write A union B as a disjoint union. How could you write it as a disjoint union? And you might have to introduce some new labels. Yes?
So you could do, I don't know if this is what you're going for, but A union B complement, B union A complement.
Okay, so if I do A union B complement,
Not A union, A,
intersect.
no, I did mean A union B
Okay,
complement.
so B complement is all the things that are not in B. So that would give me this stuff here, as well as some other stuff down here.
But that stuff isn't an A, right?
Right, but if you did A union B complement, you'd be getting too much stuff. I think you want A intersect.
B complement.
You want A intersect
Yeah, I
B
don't want
complement.
B.
So A intersect B complement is this part up here. So I can write it as A intersect B complement union A intersect B union, and there would be A complement intersect B. So that's writing it as a union of three disjoint objects. And so then I would get the probability of A union B is the probability of A intersect B complement plus the probability of A intersect B plus the probability of A complement intersect B. All right. That is a formula for the probability of A union B. It's just not necessarily the most simplified formula for A intersect B. So one of the hardest parts is trying to figure out how can you adjust the algebra? What's the nicest way to write things? And this is where it's really nice that we spend a couple of minutes trying to sniff out what a good formula might be for A union B, that we don't have to leave it like this. There's a better way of dealing with it. We have the probability of A, the probability of B, and we have minus the probability of A intersect B. All right, so I want a minus, so what I'm going to do is I've got probability of A intersect B complement plus the probability of A intersect B plus the probability of A complement intersect B plus the probability of A intersect B minus the probability of A intersect B. There are two main things you can do in mathematics. You can add 0 and you can multiply by 1. A truly exceptional proof requires you to do both. If you think back to how you proved your formulas for the derivative, what's the derivative of a sum? What's the derivative of a product? You would often add things. You would play games like that. When you have the derivative of the product, you would add 0. I want to have a minus probability of A intersect B. Well, if I'm going to subtract it off, I have to add it first. And what's nice about this is, A intersect B complement and A intersect B. What can you tell me about those two sets? It's A. But are these, I want more than just that they're A. Yes?
B complement and B is just the empty set, so you just
Well, what's true? I agree that the union of these two sets is A, but I need more than just that their union is A. I need one other thing. how do they unite to get A? Is anything double counted? It's a disjoint union. There's nothing that's in A intersect B complement and A intersect B. Because if you're in this part, you're in B complement. If you're in this part, you're in B, so you can't be in both. So this is just the probability of A intersect B complement union the probability, union A intersect B. Right. This is an extremely overly pedantic way of writing a set. Right? A intersect B complement union A intersect B. What set is that? As was said, it's just the set A. So this part here is just probability of A. And similarly, this part here, if I'm in this part, I'm not in A. If I'm in this part, I am in A. The disjoint union again. So it'll be probability of A plus probability of B minus the probability of A intersect B. And again, this is deliberately meant to be a toy example because I'm trying to illustrate an idea or a technique. By doing some work here and trying to sniff out what the formula was, it gave us an idea of how to simplify this expression. This expression is not wrong. It's just I would never want to use it. I've got a lot more intersections and complements. I've got 4 terms. And this one is defining things much easier. It's actually a lot easier to deal with intersections than it is to deal with unions. For intersections, both have to happen. For a union, what must be true? Either one. So this comes down to, what do you mean by the word or? Does anybody know the 2 definitions of or? Yes. There's the exclusive or and there's the inclusive or. The inclusive or is A happens or B happens or both happen. If you don't hear anything otherwise, you always assume it is the inclusive or. The exclusive or is at most one or exactly one happens. Either A happens or B happens, but not both. How many of you have ever done truth tables? It's a long story. I ended up not getting credit for a class I passed in college. I was put on bad academic standing. I found this out 2 weeks into the spring semester of my freshman year. I had to quickly throw a class onto my schedule. I threw on, among others, logic theory, baby logic theory. And 50% of the exam was 10 questions. It was like P and Q implies not P or Q. And the instructions said, state which of the following 10 sentences are true or false. And since this was a logic class, I debated writing, you have used the inclusive or. All sentences are truth value determinable. All sentences are true or false. Given that I was already on bad academic standing, I decided this was not a good idea to risk this. And as a math guy, it really wasn't hard to determine the truth values. But you want to be careful, and you want to make sure that you are using the words correctly. If no one says otherwise, or is the inclusive or. Be aware of that. This is why we'll often use phrases such as, it happens exactly once, versus there are exactly 2 kings in the hand, versus there are at least 2 kings in the hand. All right, this is a good place to stop.